Okay, so moving on. Um, just one other thing I wanted to mention here, just give you a better example of median versus mean. So, like we said, outliers can be problematic for means and standard deviations. However, they tend to be not problematic for median. So, for example, let's say I had these numbers here, 1, 2, that's 2, 2, not 22, 3, 3, 3, 3, 4, 4, 5. Well, the mean here is going to be 3, and the median is also 3 here. The mode, the most frequently occurring value, is also 3. So this is a normal distribution, or at least close to normal distribution. However, let's say I have those same numbers, but I also toss in 10,000. Well, now my mean is all the way up to 939. This is kind of an extreme example, but this is showing how outliers can really mess up your mean, and where median can be useful. However, the median is still going to be 3. The middle number is still 3. So when it comes to outliers, you have a couple options. Sometimes, depending on the research, it might be justified to remove them from your data. Other times, you might want to just use median. So we mentioned income. Income is probably pretty much exclusively looked at with median. Another example is reaction times. So if you're doing some sort of perception experiment, people have to like press a button as quickly as they can when they see a certain um, stimuli. Well, you tend to get outliers in their data. Like you get a specific trial where they just weren't paying attention or they checked their watch or something. Um, those can create outliers because most of your reaction times might be in the milliseconds, but then you get this one that's going to be, 1.5 seconds. Well, that can really mess up your data. It can really change your mean just based on that one kind of outlier trial. So with reaction times, you tend to use median rather than mean because it's less affected by outliers. Okay, so again, standard deviation, this is the square root of the variance, and it's often reported in conjunction with your mean. Standard deviation is important when it comes to normal distributions and bell curves because it kind of tells us how much of the data falls in a certain range. So, for example, one standard deviation above or below the mean. That's what these represent here. So that's one standard deviation above, 2 above, 3 above, 1 below, 2 below, 3 below. These, when it's a normal distribution only, tell us what percentage of the values fall within a range. So for example, 68, if you have a normal distribution again, 68% of the values are going to fall between -1 and +1 standard deviations of the mean. 2 standard deviations is going to mean 95% of the scores fall in that range. So between +2 and -2 standard deviations, above or below the mean, respectively, is going to be 95% of the scores. And then 3 standard deviation is going to be 99.7% of the values fall within that range. So again, that's kind of what we mean by when we talk about percentile. You're saying that this number falls below, or I did better than this percentage of the sample or the population, depending on what you're doing. And standard deviations kind of allow us to capture that, right? So, give you a practical example. If I was looking at, say, test scores, so an exam scores, and they were all we kind of need to know not just the mean, but we need to know the standard deviation as well. So, what's the how much do the scores actually vary? Um, so let's say I had this test and the average was like 70% and a standard deviation was like 10%. Well, that means something different than if the average is 70% and the standard deviation is, say, I don't know, only 5%, right? Because that tells us something different, right? If the standard deviation is only 5%, and the mean is 70, well then I know that 68% of the values are going to be between 75 and 65 percent correct, right? If the standard deviation is 10%, then I know that 80% or 68% of the values are going to be between 80 and 60, right? It just changes kind of the distribution. Kind of think of these plus ones and minus ones as like, what is the standard deviation? Well, yeah, that's exactly what it is. Bigger standard deviation kind of changes what the range is to some degree. But I want to emphasize that this is only true for normal distributions, so only for these bell curves. This idea of the standard of this many values falling below or above the standard deviation does not apply when you have non-normal distributions. So something like this, because it's kind of this wacky distribution, I can't say that this many, well, I could calculate it, but I can't say just based off of standard deviation that this many values is going to, you know, be within one standard deviation of the mean or below one standard deviation below the mean, right? Because the distribution is not, it's not normal, it's wacky. Same with this one here. So if you have skewed distribution, again, the rule doesn't really apply because it's not shaped normally. So the mean going, below the mean and above the mean do not really equate. Okay. So moving on, let's talk about measures of association. This kind of falls in line with reporting descriptive stats, only means are obviously for more experimental designs and quasi-experimental designs. You want to look at what were the average number of words remembered, what were the average mistakes made, whatever it might be. But we have, of course, have different, because we're not splitting people into groups, but we're looking at an association. We actually have different measures when it comes to correlations. Okay. So when measuring a correlation, and just as a refresher, hopefully you remember this, but correlation is when two variables have an association with each other. So either one goes up, the other one tends to go up. That would be a positive correlation, or as one variable goes up, the other one goes down. Okay, so something like shoe size and height. If shoe size goes up, typically height is also going to go up. Okay. So the kind of common measure of correlation is just going to be something known as R. And R ranges from 1 to 0 to -1. The negative sign here. So remember, positive, oh wait, actually I'm getting to that next. And the size of that R is going to tell you the strength or the magnitude of the association, of the correlation. Okay. So how strongly do those variables relate? So correlations, like I said, the number can vary anywhere from +1 to -1. So, and it can be 0. So what a +1 means, and you never actually get this in real research, but that means that there's a perfect correlation. Okay, a perfect positive correlation rather. If you have a value of 0, that means that there's no correlation. And anything in between is going to describe, a weak to a strong positive correlation. A correlation of -1 means that there's a perfect relationship between perfect negative relationship, meaning as one variable goes up, the other one goes down between two variables. Well, don't worry, we'll look at a bunch of examples. But yeah, the bigger the R, the stronger the relationship. Also, the sign of R again tells you the direction of the correlation or the relationship. So when we have a +1, that means there's a positive correlation. Okay, so +1 or anything positive actually means that as one variable goes up, the other one tends to go up as well. And of course, that also means that as one variable tends to go down, the other one also tends to go down. Okay, so just make sure you're clear on that. Positive correlation doesn't just mean that as one variable goes up, so does the other one, but it also means that as one variable goes up, or sorry, as one variable goes down, the other one also goes down. So basically, they're going in the same direction. Okay. Now, on the other hand, if the sign is negative, so we have a negative R, that means that there's a negative correlation. Okay. And that means that as one variable goes up, the other one tends to go down. As the same variable goes down, the other one tends to go up. Okay. That's what the sign tells us. So here's another illustration of that. Again, it's positive. If the R is positive, that means that as A goes down, B goes down, and as A goes up, B goes up. They're both heading in the same direction. Negative would mean that, again, they go in opposite directions. So as A goes up, B goes down. A goes down, goes up, opposite. Just again, give you kind of a real world example. Let's say positive correlation would again be as shoe size goes up, height goes up. Shoe size goes down, height also tends to go down. For a negative correlation, let's say, number of drinks consumed and GPA. As number of drinks goes up, GPA goes down. Number of drinks goes down, GPA goes up. Okay. So, and then the other piece again is going to mean that what is the magnitude of the relationship? So a bigger R means that there's a stronger relationship, or rather, a bigger absolute value means there's a stronger relationship. So -1 means there's a closer to -1 is a stronger, closer to 0 is weaker. Closer to 1 is stronger, and closer to 0 is weaker. So let's look at some examples here. You don't need to write all these down. There's a bunch of them, but this is a zero correlation, meaning there's no relationship between these two variables. As you can see, there's no trend between x going up and y going up. They're just kind of randomly distributed. There's also no negative correlation because as x goes up, y does not go down. Okay. Now, looking at the other end of the spectrum, this is a near perfect correlation. So as x goes up here, y goes up almost in an identical manner. So notice how kind of these dots are all almost perfectly clustered around this line here. Okay, that would be an almost perfect correlation. As one goes up, the other one goes up in an almost perfectly predictable manner. So that's kind of another way to think about this, is if there's a perfect correlation, that would mean that as x goes up, y is going to go up, and you can predict exactly how much y goes up based on x. And the weaker the correlation, the less prediction you can do. So with, say, this 0.2 correlation, I can predict a bit, where a y point will be based on x, but it's not very accurate because it's a weak correlation. There's a line there, there's a relationship, but it's very weak. And this is all the stuff in the middle. So 0.8, obviously, pretty strong correlation. We can predict a lot of y based on x. Here we can predict less, so on and so forth. So these are all positive correlations. It's the same idea though, just with negative. So if this line was going that way, but it was like a perfect cluster around the line, and I could predict all the change in y from x, well, that would mean that'd be a perfect negative correlation. A weak negative correlation would be this, or any of these, but just the line going in the opposite way. So if the line was going the opposite way, that would mean that x is increasing, y is decreasing, making it a negative correlation. Okay. And again, so yeah, the positive or negative value tells you what's the direction, and then the value itself tells you how strong is it. The closer to either 1 or -1 it is, the stronger, the more predictive it is. The closer to 0 it is, the weaker it is. Okay. So let's see. So typically when you want to plot a correlation, you'll use a scatter plot. When you do that, each point is going to be a single participant's data. So let's say again, I was looking at shoe size and height. Well, what I would do is I take a whole bunch of people and get their shoe size and get their height. And then each participant would have an X and a Y score. Okay, so they'd have two scores, two variables, shoe size, height. What you then do is you're just going to plot those two things, and each individual point on the scatter plot is going to be a participant score on both those values. So let's say this point here, that's going to be one participant who had, I don't know, size 9 shoes, and they were, I don't know, this tall, 5'9". This participant here had, let's say, size 15 shoes, and they were 6'5". That's what's going to happen here is, again, you're just plotting each individual point. Their score on one variable goes on the x-axis, and then their score on the other variable goes on the y-axis. Okay? Each of these represent individual participants. This, by the way, plotting a scatter plot can be useful because it can reveal outliers. So oftentimes, not just with kind of mean measures and stuff like that, even looking at correlations, sometimes you have an outlier. So here we have a pretty strong correlation. So as A is going up, B is also going up in a very similar fashion. But there might be one value that's just completely opposite of what the rest of the data is showing. And this can, of course, weaken the relationship. Okay. So if we were to get rid of this value, we'd have a much stronger correlation just looking at these. If we include this value, it weakens the relationship. Okay. Now, what you want to do about that, whether you can get rid of the participant or not, kind of depends on your research. That's a whole other thing. But for now, just bear in mind that extraneous variables or outliers can really weaken a correlation like this one here. And scatter plots can help you spot those. Okay. Another key thing to keep in mind when you're dealing with correlations is something known as restriction of range. And this is any time you basically don't have enough of a range of the value you're looking. So to give you an example, and this can be a problem for measuring association. So for example, say I wanted to look at test anxiety and test performance. So when people take a math exam, does their anxiety predict their performance? Is it correlated with their performance? We would expect a negative correlation there. The more nervous someone is, the worse they're going to perform on the exam. The less nervous they are, they're probably going to do better. Well, an issue there and a restriction of range might be if anxiety is very restricted to a certain range. So, for example, maybe you only get people with really high anxiety doing the study, then you're kind of getting a very restricted range of what actual anxiety variables, what the actual anxiety variable could be in the population. Okay. Maybe you have the opposite problem of anxiety is quite low. So the range of anxiety you can actually include in your study is very low and not really representing what you want. You're not getting people in your sample who have both high and low and everything in the middle in terms of anxiety. You're only kind of getting one piece of that. Okay. That's actually something that often comes up in my cognition lab. So if people want to do experiments involving anxiety, they often end up with people just very low levels of anxiety. So like everyone's kind of the low end of the spectrum. So it doesn't really, not really a lot we can do with it. Here's another example. Let's say you looked at correlation between grip strength, arm strength, and some workers. It might kind of the one end of the spectrum, maybe the higher end of the spectrum, or the lower end of the spectrum. It could really be either. Might not give you a good correlation. So if you're just looking at, say, kind of the lower end, or sorry, no, this is the top end on the bottom here. That actually gives you a weaker correlation than including the whole range of, say, 20 to 100, like we want. So bottom line is you want a good range when it comes to your correlation. You want everything high, low, in the middle, okay, rather than just kind of one section of that. Okay. That's it for now.